Process management is one of the fundamental pillars of Linux system administration and security. Just as you have learned to control who can read or write files through permissions, you now need to understand who is running what on the system, with what privileges, and how to influence those processes. In a security context, the ability to inspect, prioritize, and manage processes is critical. Attackers often plant rogue processes, escalate privileges through running services, or consume resources to cause denial of service. Knowing how to detect and respond to these situations is an essential skill for any cybersecurity or DevSecOps specialist. A process is simply a running instance of a program. When you type a command like ls or launch a web server like Apache, Linux creates a process for it. Every process is assigned a unique identifier called a process identifier, or PID. Alongside the PID, each process also has a parent process identifier, PPID, which tells you which process spawned it. This parent-child relationship forms a tree structure that can reveal a great deal about what is happening on a system. Every process runs under a specific user account. This is directly connected to what you have already studied about permissions. A process inherits the effective user identity of whoever launched it. If a process is running as root, it has unrestricted access to the system. If a malicious program manages to run as root, it can read any file, modify configurations, create users, and do virtually anything. This is why monitoring which processes run as root is a key security task. The PS command. The PS command, which stands for process status, is used to display a snapshot of the currently running processes at the moment you execute the command. It does not refresh automatically. It simply takes a picture of the process list at that instant. Used without any option, PS shows only the processes associated with the current terminal session. This is rarely what you want in a security investigation. The most commonly used form is PSO. Here, a means show processes from all users. U means display in a user-oriented format, showing the user, CPU usage, memory usage, and more, and X includes processes that are not attached to a terminal, such as background daemons. Daemons are long-running services like web servers, database engines, or logging services. The output of PSO includes the following columns: user, the account under which the process is running, PID, the unique process identifier, %CPU, the percentage of processor time the process is consuming, %MEM the percentage of memory the process is consuming, VSZ, the virtual memory size allocated to the process, RSS, the resident set size, meaning the actual physical memory in use, TTY, the terminal associated with the process, a question mark means no terminal, typical of daemons, stat, the process state, explained below, start, when the process was started, time, the total processor time consumed, comment, the command that launched the process. The stat column is particularly useful. Common values include R, the process is currently running or ready to run, S, the process is sleeping, waiting for an event, most processes are in this state most of the time, D, the process is in uninterruptible sleep, usually waiting for input/output from a disk, Z, the process is a zombie, it has finished executing but its parent has not yet collected its exit status, T, the process has been stopped, for example by a signal, S, this process is a session leader, plus, the process is in the foreground process group. Zombie processes are worth noting from a security perspective. While they do not consume processor resources, a large number of zombie processes can indicate a poorly written application or a parent process that is not cleaning up properly, which might hint at instability or exploitation attempts. Another very useful form of PS is PSF. Here E selects all processes and F gives a full format listing. This format explicitly shows the PID, parent process identifier, making it easier to reconstruct the process tree. You can also use PSF forest. This displays the parent-child relationships in a visual tree format, which is extremely helpful when tracking how a suspicious process was launched. For example, if you see a bash shell process whose parent is a web server process, like Apache, this is a strong indicator of a command injection or web shell attack. The top command. While PS provides a static snapshot, top provides a live, continuously refreshed view of the running processes. By default, top updates every 3 seconds and sorts processes by processor usage, showing the most resource-intensive processes at the top of the list. The top section of the top display shows system-wide summary information. The uptime of the system and the number of logged-in users. Load averages for the past 1, 5, and 15 minutes, these indicate how busy the system has been. The total number of tasks, processes, and how many are running, sleeping, stopped, or zombies. Processor usage broken down into user space, US system/kernel space, SCI, nice, ni, idle, waiting for input/output, wa, hardware interrupts, hi, software interrupts, c, and stolen time from a virtual machine, st memory usage in terms of total, free, used, and buffer/cache memory. Swap usage. The bottom section lists individual processes with columns similar to PSO, including PA, UZR, priority, PR, nice value, ni, virtual memory, VIRT, resident memory, RES, shared memory, SHR, process state, S, processor percentage, %CPU, memory percentage, %MEM, time used, and the command. Useful interactive commands while top is running. Press Q to quit. Press K then enter a PID to kill a process. Press R then enter a PID to renice a process, change its priority. Press U then enter a username to filter by user. Press P to sort by processor usage, the default. Press M to sort by memory usage. Press H to see the help screen. From a security standpoint, top is useful for quickly spotting a process that is consuming an abnormal amount of processor time or memory. A cryptometer planted by an attacker, for example, will typically appear at the very top of the list in top due to its high processor consumption. Similarly, a process consuming nearly all available memory might be part of a denial of service attack. A related command, ethtop, is not always installed by default but provides a more user-friendly, color-coded, and interactive version of top. It allows mouse interaction and easier process management. Understanding process priority and the nice command. Linux uses a scheduling system to decide how processor time is distributed among running processes. Not all processes are equally important. A database service might need more processor time than a background logging task. Linux uses a concept called the nice value to express this relative priority. The nice value ranges from -20, the highest priority, meaning the process gets the most processor time, to +19, the lowest priority, meaning the process yields processor time to others. The default nice value for a new process is 0. A nicer process, higher nice value, is more willing to yield processor time to other processes, hence the name. Only the root user can set a negative nice value, which increases priority. A regular user can only make their processes nicer, increase the nice value, thereby lowering priority. This restriction is important from a security perspective. It prevents unprivileged users from monopolizing the processor. To launch a command with a specific nice value, use nice n10 my_script.sh. This starts my_script.sh with a nice value of 10, meaning it will have lower priority than normal processes and will not compete aggressively for processor time. This is useful when running resource-intensive background tasks like backups or log analysis during business hours. To change the nice value of an already running process, use the renice command. Renice n5p 1234. This sets the nice value of the process with PID 1234 to 5. Again, only root can set a negative nice value or decrease the nice value of a process it does not own. In top, the ni column shows the current nice value of each process, and the PR column shows the actual scheduling priority as seen by the kernel, which is typically 20 plus the nice value, so a nice value of 0 corresponds to a priority of 20. Security relevance of process management. From a security and DevSecOps perspective, process management skills are directly applicable in several scenarios. First, detecting unauthorized or suspicious processes. After a system compromise, attackers often run hidden or disguised processes. A common technique is to name a malicious process with a name similar to a legitimate system process. By carefully examining the full command path and PSO output, you can spot anomalies. For example, a legitimate SSHD process runs from /user/spin/sshd, while a fake one might run from /tmp/sshd. Second, identifying privilege escalation through processes. Recalling what you learned about setuid bits, a process launched from a setuid binary will run with elevated privileges. Using PSO and inspecting processes running as root that were launched by a non-root user can reveal whether a privilege escalation has occurred. Third, detecting resource abuse. Cryptominers and botnet agents are typically detectable through high processor usage visible in top. Sudden unexplained processor spikes are a red flag. Fourth, understanding the attack surface. Every running service is a potential entry point. By listing all processes and identifying every listening service, you build a map of the attack surface. This is a prerequisite for a proper penetration test scoping phase. Fifth, in a continuous integration and continuous delivery pipeline, Runaway processes during automated test stages can be detected and terminated using these tools, preventing resource starvation that would delay deployments or mask test failures. Practical examples. Example 1. You want to check if a web server is running as root, which would be a security risk. You run pso, grep apache and see the process listed under the root user. This is a misconfiguration you would flag immediately. Example 2. You notice the system is slow. You run top and observe a process called smurrig consuming 98% of processor time. You do not recognize this process. You press K in top, enter its PID, and terminate it. You then investigate how it got there. Example 3. You need to run a large file compression task on a production server without impacting live users. You run nice n15 tar czf backup.tar.gs/var/www/html to ensure the compression task yields processor time to other processes. Example 4. You see a process with stat z, zombie. You use PSF to find its PEPID and investigate the parent process. If the parent itself has crashed or is misbehaving, this might require a restart of that service. Example 5. You run PSF forest and discover a bash shell process whose parent is the nginx web server process. This is a classic sign of a remote code execution exploit. An attacker has managed to run shell commands through the web server. This finding would be documented in a penetration test report as a critical vulnerability. Mastering these three tools, PS, top, and nice, gives you the visibility and control needed to monitor what is running on a Linux system, respond to incidents, and reduce the risk surface of any application environment.